So we've talked about existence proofs, but there's also uniqueness proofs. So you might recall that we had a symbol that looked like the following. And here I'm using y instead of x, and you'll see why in just a second. So here, this is, there exists a unique y such that my statement P of y is true. And why might this be useful? Well, let's say that you're trying to design an algorithm and it returns a result, and for some reason it's very important that that result is the only possible solution. So in cases like that, when you want your algorithm to return a result and you want to be sure that that is the only actual result that you're going to get, then uniqueness proofs are going to be very helpful. So one thing that we haven't actually discussed about this particular symbol right here is that it's actually logically equivalent to the following. Okay, so there's a lot of parentheses here, but let's go ahead and break down what this is saying. So there exists a unique y such that P of y is equivalent to this nice compound expression. So what is this compound expression saying? Well, there are a couple of parts to it. So first off, there exists a y such that P of y. So this part right here shows existence. And then what does this part say? Because it's and then this part. So this part says for every other variable, if your statement P of z is true, then z equals y. So it says for every other variable z that makes your propositional function true, that one is actually y. So what this part says is the uniqueness. So for any uniqueness proof, it's basically going to break down into two steps. One is you actually have to go and find one that exists, and the second step is you have to show that it's the only one. If there's any other solution, then it's actually the one that you originally found over here. So let's go ahead and see this uniqueness proof strategy in action with the following example. So we want to show that for all real numbers x not equal to 2, there exists a unique solution to this particular equation. And so trying to find a unique solution, so the x here is given to us, so what we're trying to find is we're trying to find a unique y that satisfies this equation here. So in particular, this can be thought of as our propositional function P of y. And that's indeed why I used a y up here, because this particular example uses y as the thing that we're trying to find existence and uniqueness for. So as I said, for a uniqueness proof, we need to break it down into two steps, existence and uniqueness. So let's go ahead and start out this proof. So the first thing that they asked us is to show that for all real numbers x not equal to 2. So let's assume that x is not equal to 2 and it's an arbitrary number. So let's let x not equal to 2 be arbitrary, and then, as I said, two steps. So the very first step is we have to show existence. Well, we've already talked about existence proofs, right? We have constructive and non-constructive existence proof techniques. And in this case, it actually turns out rather easily that we can give a constructive example of an existence of a y that satisfies this particular equation. So let's go ahead and consider the following. So let's consider y equals x over 2 minus x. And you can see why it's important here that x is not equal to 2, because otherwise we would have division by 0 right here. So let's consider that. And what we want to show is that p of y is true. So p of y, remember we're doing this part, this existence part, we're trying to show there exists a y such that p of y is true. That means that I have to plug this particular y into this equation and see if it's true. So I want to take this y, plug it in here, and see if it's equal to x. So let's go ahead and just do that. Okay, so we have 2y over y plus 1. I'm going to take this and I'm going to plug it in wherever I see y. And I got to do some simplification right here because remember I'm trying to show that that's equal to x. So first off, let's find a common denominator here. Okay, found a common denominator. Let's go ahead and add these things together. The numerators, the x and the minus x, those cancel, so I'm going to get a 2 on the bottom. And now I got a bunch of nested divisions right here, but you'll notice that I have a 2 minus x and a 2 minus x here. Those are going to cancel out, and so what I'm going to end up with is 2x over 2. My 2's cancel, and I end up with an x. Yes, fantastic. That means that my equation actually is true. If I let y be that particular value right there, then my p of y is true. So I've been able to plug in that particular value of y, and I showed that it was equal to x, therefore this p of y statement is true. So that just showed the existence part. We still need to show the uniqueness. So for the uniqueness, I have to show that that statement right here is true. So for the uniqueness, what I want to do is I want to prove that for every z, if p of z is true, that means z equals y. And which y? That particular y that I constructed in my existence step. So this is just a standard implication. And we have a bunch of different proof techniques that we can use to be able to prove this. So I'm going to go ahead and proceed by direct proof. So if you recall, for a direct proof, we need to assume the hypothesis. So assume that p of z is true, and I want to show the conclusion that z equals y, that y. Well, what is p of z? That was this equation right here. So what I'm actually assuming is 2z over z plus 1 equals x is a true statement, that that equation right there actually holds. So now what I want to do is I want to show that z has to equal y. So let's go ahead and see if we can't isolate z and see if it turns out to be that expression. And thankfully that's just a little bit more algebra. Let's divide through by z plus 1. So oftentimes my 2's and my z's look similar, so I'm going to start putting a little horizontal bar through my z's so you can tell the difference between a 2 and a z. But in any case, so I've expanded this thing out. Let's isolate the z's on one side. Factor out a z. Divide by 2 minus x, and here again, it's really important that x is not equal to 2. And aha, check that out. We have z equals x over 2x. That's exactly what y is. So therefore, by a direct proof, I was able to show the uniqueness part. So in summary, uniqueness proofs are very similar to existence proofs. You have just one extra step. So after you show the existence, you just have to show uniqueness. And that uniqueness boils down to proving this statement. Any other solution turns out to be the one that you found in the existence part. And that's all a uniqueness proof needs.